Hi, I'm Hanneli. I'm from Brazil. I am a software developer, and as our friend told us, I started the Rust meetup in São Paulo area. Today we have around 300 members, which is something. We have been running the meetups for around 1 year, and I'm very happy to say that we can provide a meetup almost every month, and I'm happy to see the community growing, and usually we have some volunteers to present some interesting topics, such as implementing genetic algorithms with Rust, implementing the basic concepts of the language with Pokemon. I had this talk, so I'm very happy to see the community growing. And during my free time, I like to do these things here. I like coffee and gifts and Pokemon. So if you're playing Pokemon Go, we can walk around the city to catch some Pokemons. So this presentation is about rewriting some frequently used codes in a tool called Octave. If you're not familiar with Octave, I'm going to talk about this tool in the further slides. But as a bonus, even if you're not working directly with Rust, I expect that by the end of this talk, you have a general idea about transforming some math concepts into code in a very expressive way or in a more intuitive way. This is a quick disclaimer. This talk contains some code prototypes. I'm going to show you step by step how we started building some code in Rust for Octave. So this is going to be kind of, just a draft. So there is some code that actually doesn't run. Into the last slide, I leave you some reference, so you can actually get the code from GitHub and run it. There's going to be some mathematics. I know it's the last talk of the day, so please hold on, keep firm. I think nobody's going to be scared about the math that there is at this presentation. And to help us to keep firm until the dinner time, we are going to see some cat gifs, because cat gifs are nice. So quick agenda. Let's start talking about some training tools in science. Oops. Training tools in science are becoming very popular, and this is kind of the motivation. Oops, missed this slide here. And this is kind of, probably you have contact with some of these tools based on Coursera. I think everybody here doesn't know what's Coursera. Doesn't. I mean, Coursera is very popular. EDX is another popular too. So these platforms, they are bringing content from academia to people who are just maybe web developers or people who do not have a strong background in research, which is pretty cool. It's pretty exciting. And oops, I think I'm having some trouble with, yeah. And this is like bringing topics such as machine learning, data analysis, big data, to people who are not tightly connected with research, which is pretty interesting. And so I was talking to some students at the university that I graduated at, maybe last year, something like that. And they were telling me that they use some of these tools to help them with mathematics. So one of these famous tools is Octave. Octave is pretty much has pretty much the same purpose of MATLAB, and it can help you if you are, for example, electrical engineer trying to solve some crazy and differential equations who are very difficult to solve by hand, and you need a software to provide you some support. And I was talking to the students, and I asked them if they like Octave. I pretty much like Octave, but I had some difficult time during my undergrad years when I was doing research. So usually I had a problem to resolve, like, I don't know, low frequency inversors that I had to figure out how to implement that into a circuit. But if I went to Octave, I would spend a lot of time with things that had nothing to do with the problem that I had to solve. For example, I was getting a dangling pointer at some point, or I forget to deallocate memory and everything blows up. So that was kind of frustrating to me. I'm not saying like this happens to everybody, but I have a very hard and difficult time with this tool, and pretty much all the other tools who are open source would provide me the same problem. So I really liked the tool, but I had some trouble with that. I had trouble to extend the functionalities of the tool. And I was surprised because when I asked the students if they liked the tool, they said yes, but we have trouble to express mathematics with C and C++ in Octave. So that's the case that you end up losing a lot of time with something else rather than spending time with your problem. And then we started to think about the possibilities that we could adopt to resolve it. And I was studying Rust at that time. Version 1.0 was just released. And then I asked them, oh, have you tried Rust? And they asked, oh, no, what's Rust? And then I said, oh, I think I can borrow you some knowledge. Oh, is it safe? Please laugh. But no jokes. I spoke to them about Rust, and they accepted to try the language and see if it could help them with the problems that they were facing. So Octave, if you're not familiar with the tool, is pretty much useful for machine learning, for data analysis, for, I don't know, maybe some calculations that it needs to do with computer vision and things like this. It's useful for example, operations with matrices, plotting charts, statistics, and several other areas that have some heavy calculations that you don't want to resolve everything by hand. A good point about Octave is that it is open source, and open source is pretty cool because you can easily extend the existing libraries, you can submit patches and things like this. And this is pretty much what happens when you're doing research. There is a point that you need to add your code to an existing tool. So for example, there are lots of external packages that people built for Octave, and they are available on GitHub or any other source repo. And then you can easily, add your contributions to the tool, which is amazing. But sometimes it's not easy to handle the format that the tool is available for you. Let's discuss something like this. A very famous data structure is this one. It's very likely that one day, at any point of your life, you receive this spreadsheet. A spreadsheet. And a spreadsheet is a table. So we have to handle tables, or better, matrices, in several scenarios, several distinct scenarios, right? But why matrices are so important? So because everybody sends me spreadsheets. No, not only because of that. Matrices, they can represent several different areas, and sometimes you're not aware that you can represent something with a matrix, but you actually can. So I guess one of the first contacts that you had with matrices was at high school, but sometimes not even in mathematics, in math classes. It was something else. Do you remember this law here, Ohm's law? You have this circuit, and then you have the voltage, and then you have this relation between the resistance and the voltage. And then you can make this even more sophisticated. I'm happy because I saw talks about circuits today, so I guess nobody's scared of this. This is, very simple circuit, and then if you remember this, oh no, even if you failed on physics class, you might remember something like a circuit with voltages and values for the resistance. By the way, those are the Kirchhoff laws. And Kirchhoff laws are an example of what we call linear systems. And for example, this is a linear system. You have a bunch of equations, and you have to resolve these equations, find a value for every variable that you have involved in the system. So you can, do some algebraic work and figure out the values for the resistance 1, 2, and so on. But for linear systems, there is an alternative representation rather than this one with the curly brackets, we can represent them as a matrix. And there are lots of advantages of representing linear systems as matrices. We can apply several different rules. For example, there is what you call determinants. There is what you call, several different rules for finding properties of a linear system. So understanding a little bit about matrices helps us a lot to resolve linear systems. And linear systems, they are a structure which you can find in several different areas. For example, electrical engineering, environmental engineering, how the environment behaves and things like this. And for example, this is part of the code that you have to represent an array or a matrix in Octave. This is the code base for array, and there's a class called matrix. This is a very extensive code. It has around 500 lines, something like that. And it's pretty much about template declaration. So I suggested the students, so I asked those students that I was talking last year, I asked them, what is the most frequent structure that you use in Octave? And they said, matrix. And it's most of the cases you have to extend a matrix to implement something for you, or at least implement some sort of calculation for your matrix. So I suggested them, why don't you start building a matrix in Rust? So I need your help. How would you build a matrix in Rust? Please say something. Vector. Okay, but a vector is too general. How would you build your own struct? Come on, you know that. Struct. You need a struct, right? Let's build a struct called matrix. Makes sense. Makes a lot of sense. So tell me, what's going to be into this struct? Think about a matrix. Numbers. Think about this matrix here that you are seeing on the right side of the screen. Rows. If you have rows, you have columns. And there is something inside the matrix, which are the matrix elements. That makes sense, and this is simple. This is the very first step that you might have if you're trying to build a representation of a matrix, right? That makes a lot of sense. So I was talking to these students, and we came up with this brilliant and super sophisticated matrix struct. But we started discussing something else. So for example, if you remember your math classes, when you multiply matrices, can you multiply any matrix with any other matrix? No, there is a rule. So on the right side, you have a matrix with 2 rows and 3 columns. On the left side, you have a matrix with 3 rows and 4 columns. Can we multiply this matrix? Yes, because the number of columns of the first matrix is equal of the number of rows of the second matrix. So yes, we can multiply these 2 matrices. What's going to be the dimension of the output matrix? 2 by 4. Great. So you have some rules based on the matrix dimensions. Interesting. I have a question for you. Do you remember our matrix structure? Can we easily represent this property with this struct? Can we? We can. We have to keep checking the dimensions every time. But this is what you do in C++ because of the template. So you have to keep checking all the time. This is not very convenient. How can we improve this code? We want to add some behavior into a structure based on its dimension. So this is a bad representation. Don't do that. Instead, create a trait called dimension. That makes a lot of sense because you can add all the behavior based on the dimension of a matrix inside this code. And this is going to be much more explicit. When you give Rust a matrix with a certain dimension, Rust can determine at compile time if it's going to work or not. You don't even have to spend time trying to, perform an invalid operation with matrix with dimensions that do not match. This is pretty interesting. And then we can also add an extra step. I was reading something at the internet. I think I have a pointer. No, I don't. So there is a link at the bottom of the page, and he suggested that we should use phantom data when we are representing a matrix, and that makes sense. Can you picture in your head a matrix without any element? Doesn't make much sense. Sorry? Yeah, but there is no matrix without a named set. No. So this kind of thing doesn't exist. And this author, he was saying something like, well, you should always have an element representation, which you can do by using phantom data. Or you can create your own type of a matrix element. Kind of doesn't matter. But this representation of a matrix is kind of much better and much more well-structured than our initial representation, where we had rows, columns, and something pretty vague for data. This is pretty interesting. And this is actually how the ND array is implemented. They use some structure like this to represent any kind of array. Any kind of array has a dimension and element set. An extra challenge. Can you think of codes to represent square matrices? Does it make sense to have a code for square matrices in terms of the common and most used mathematical properties that you have for matrices? Yes, it makes a lot of sense to create your own specialized squared matrix based on a matrix itself. So this is pretty cool. You can fix the dimensions. So the dimensions for rows and column are always equal, and then you can derive a bunch of code from this initial code. So this is pretty convenient for us. And with that, I hope you had a very quick overview of why linear algebra is important and why matrices are important. And I really hope that you could have followed the main idea of how we get a mathematical concept and we apply this to Rust. That was our very first attempt. And the final code that the students were using was pretty much like this one. And everybody's kind of happy with that. Another important structure that students or researchers use a lot, complex numbers. If you come from engineering backgrounds, you're very likely to have seen a lot of complex numbers. Do you know why? There is a reason for people keep using complex numbers, but do you know why? I mean, a good explanation, because they like it. Oh, because there is an imaginary part and this is cool. This is not a good, this is not a good point. For example, quantum computers, which is a very nice subject, everything is based on complex numbers. What's the reason for that? It's easier to differentiate. Yes, that is one point, but you can differentiate real numbers as well. Makes the math, why? Of -1. But there is a more generic reason to use that. Let's talk about this. This is kind of the off-topic moment of this lecture, but I hope that after this session you share with everybody why you use complex numbers. Yes, but why? There is a single mathematical reason for this equivalence. Why does it exist? This is true. That makes everything much more simple. Let's talk about this. So, let's start from the beginning. Integers. I'm happy because at the very first keynote on this morning, we were talking about integers and real numbers. but we didn't reach the complex numbers, which are so important. So when you add an integer to another integer, what is the output? An integer. I'm glad it's an integer. So when you're talking about the add operation between two integers, the output is equal to the input in terms of type. But that's not true when you're talking about the division. If you divide an integer by an integer, what happens? You may not have an integer as a result. May not. There is a chance that it is, but there's a chance it's not. So what happens here is like you have more restrictive sets and more wide sets. So if you check at this picture, which I added the letters that correspond to each set by hand, it's pretty ugly. I'm sorry about that. But if you look, there is a set involving all the other sets, which, if you're not familiar with all the sets, you can easily, copy this concept from the keynote that we had this morning. So, what is the most inclusive set that we could be using based on this? The real numbers. Okay, cool. All the numbers. Yeah, yay. So if you get a real number, and if you divide, subtract, multiply, or add, you always get a real number as an output. Oh, what happens if you divide by 0? But 0 is an exclusion. Don't consider that. There is something even more generic than dividing by 0. Is there any other operation that you can think of? Somebody already told the answer in the audience? Yes, there is an operation that you provide a real as an input, and you might not end up with a real as the output. This one. When you're looking for the square root of a number, if you're looking for the square root of -4, the result is not going to be a real number. So this is sad. So the thing here is like complex numbers. They have this property that we say they are closed for the most common algebraic operations. So if somebody says that, oh, this operation is closed, you can be sure that the input is going to be as the same type of the output. And this is very convenient for functional programming, for example. If you're talking about types, the friend here in the front already talked about the types. This is very convenient because you can be 100% sure of the output, the type of the output. And you can, derive lots of things on type theory about that. Can we express this property with code? Yes, it's not difficult. For example, you can have this structure here called complex number that has the real and the imaginary parts. And all the mathematical operations are going to result in a complex number, something like this. This is pretty much straightforward and convenient. But why is this important? Well, if you think about creating a trait called closed set, you can add this trait to your existing types and make sure they are closed operations in a certain scope, which is very convenient for several operations in engineering. Sometimes in engineering, you want to be sure that the output is going to be equal to the input. This is much true for control systems engineering, for digital signal processing, and things like this. This is very convenient. So think about it. Rust is very powerful because with a trait, you can add a behavior given a certain scope, even for existing types. So you don't have to, create new types just to represent that. And this is very convenient for engineering. Why is anybody doing that? I mean, there's probably somebody doing that, but the biggest tools that you have for engineering, they still using, just imperative programming with some languages that sometimes you cannot have this level of, you cannot be very expressive with the tools that the language provides to you. I don't know about you, but I was so excited when we did that I started rewriting some codes that we had for control systems. And this is very convenient. You just create a trait and add to an existing type that you had previously. Happy thing here is that the complex numbers are already part of num, so you do not have excuses to keep using open sets for your most common operations. How much? Okay, so I think I still have time. I don't know who's counting the time, but some lessons learned. They're really great tools to help, mathematics in terms of engineering and general science. But I don't know about you, but I've been struggling with these tools for a long time. Besides MATLAB and Octave, for example, we have VHDL. It's a language that describes hardware. And if you think about VHDL, couldn't we be using Rust to describe hardware? I think based on the sessions that I had today, yes. But could Rust become a substitute for VHDL? Maybe yes. 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 So I don't know about you, but I had a very hard time with some trouble that I found at VHDL that I simply could not represent that based on the language. And maybe with Rust, we could do something to improve, our expressiveness over the system in general. For me, it was pretty sad to change my focus. I was trying to solve a problem. How can I optimize the trails of the circuits, and I should resolve this and this and this. And from time to time, I was losing focus trying to solve dangling pointers or something wrong that I did in the middle of the code. So that was not very productive to me. That was kind of consuming time from my research with something that should be draining my time of that research. And I had a very difficult time to express some sorts of types. Sometimes I wanted to add some behavior to an existing type, so I had to create another class with another set of descriptions and things like this. And with Rust, I don't have this problem anymore. And one last thing, like when I learned how to program, object-oriented programming, the examples were like with animals, so like class animal, and then class dog extends animal. But nobody taught me how to transform mathematics, which is a useful thing for engineering, and code. So nobody taught me like, hey, here is a different differential equation, and now you get this equation and transform this into C. They started saying, oh, now you have to use numerical methods because you cannot represent that. Of course you can represent that. Maybe I was just using the wrong paradigm and the wrong language, but there is a way to represent these mathematical structures in a more natural and straightforward way. And I found out that Rust was really helpful to solve most of these problems that I was having. And one last but not least point, I was so happy that the compiler was telling me that something was wrong before I run it. Something very frustrating to me is like Octave can be slow for some operations, and I was running an operation in Octave, and boom, runtime error after 10 minutes. I wanted to cry. I lost 10 minutes to get a runtime error. I was really sad with that. And some of these problems can be avoided with Rust because with the certain types, the Rust compiler can tell you, hey, don't do that because it's wrong. One last thing about these runtime errors is like, I don't have this responsibility anymore. I just, throw this responsibility to the compilers in certain cases. Of course, like there are cases which you can't do anything. And one conclusion that I took from there, talking to the students, is like, well, why don't you have many people doing that? So we have concepts and mindsets that, based on this talk, that can be applied to other areas. For example, the idea of closed set, it's a mathematical concept, but we can apply that to, maybe payments. Think about it. So maybe you can, if you can describe a mathematical property more easily and more straightforward in a programming language, maybe we can start using lots of mathematical concepts in our daily basis. Sometimes I see lots of young people asking, oh, why do you have to study calculus and all these things? And sometimes it's not obvious how could you be applying these concepts in real life problems, in, I don't know, maybe problems of web developments, or I don't know, payments or products and things like this. But if you had a more convenient way to describe mathematics into programming, maybe we can spread this knowledge across other areas of the industry, and maybe we can make them more popular. Well, that happens. Fail happens. So I shared the good parts, and I'm going to share the things that went wrong, or almost destroyed my project. So when I started learning about Rust, I said, oh, there's this thing called unsafe, and I probably will never use that. But if you need to integrate Rust with another language, sometimes you need to use unsafe. And I found myself, like, every time that I had a problem, I just typed this magical word at the beginning, and things were working. Okay, it's not working with safe, let's try unsafe, and it works. This is not a good idea. I mean, at all. It's a terrible idea. So sometimes, yes, if you're doing a fallback to C or any other language, Python, anything else, there is no, you can have your unsafe methods or your unsafe function, but you should not expose that. So if you have something unsafe, do this inside a safe method, and let the method handle all the possible problems that you might end up with. And I'm telling this because I was aware of this, but my body refused it to do, because it was much more convenient just to type the unsafe until somebody uses the library and say, oh, everything is broken. And I was like, why? It works on my machine. So make things safer. It's a good advice. There was another example, again, unsafe and mute. Oh, if it's not working, just add mute and everything will be fine. This is awful. And I did this lots of times. So if you're familiar with a fast Fourier transform, an FFT, basically the idea of a fast Fourier transform is get a signal which is represented according to the time domain, and transform this to the frequency domain. So you're doing a transformation. That's why you can see on the screen at this first line here. So you have a function called from time that gets a signal which is represented on time, and you output that as a signal based on frequency. And the same for the reverse case. You have a signal represented on frequency, and you want to fall back to signal in time. So I was using some libraries, and I was having trouble because my input was not working. So I decided to pass a mutable instance, which I'm happy with that. But in terms of concepts, it doesn't make sense. Your sampling is something immutable. Once you have the sampling of a signal, it's never going to change. So it doesn't make sense in terms of coding. So I was writing a convenient code in terms of programming, but it's a code that doesn't make sense at all in terms of representation. So when you're going to write your tools for science or engineering, think about that. Think about, oh, wait, does it make sense? It doesn't make sense to represent a mutable signal with mute, for obvious reasons. It's much better to remove the mutes and actually handle your struct into the appropriate way, not base it into the easy way. So I'd like to leave some references here. I was kind of happy to see that Servo has Euclid, which is a tool for linear algebra, and I was reading the source code. It's very interesting. The second line is the ND array. So you can actually find some structures that are pretty much the same as the ones that we saw at the beginning of this presentation. You're going to see that instead of phantom data, they are using a default matrix instead. But they have a bunch of interesting approaches to handle any kind of array of n dimensions. There's also some papers about Rust types and how these types can help you with science tools. It's the FTP link that you see there, and of course some well-known references like the num, like the docs, and there is one very interesting and probably also well-known one. I don't know if I added here. No, I didn't. I can add later. It is a tool about FFT in Rust. So what else? So some special thanks to Florian. I'd like to add a picture of Florian saying, no more puns, but maybe next time. And for Bruno from Brazil, Bruno is also helping the Brazilian community, the Rust Brazilian community, and for ThoughtWorks, because ThoughtWorks has been hosting most of our meetups. For my mentor, Daniel, and for these people who provide me gifts, and of course for the Brazilian Rust community. And thank you, and I don't know if we have time for questions. We don't have time for questions. Thank you.